Hey guys, welcome back to day 25. We're talking about polarity in molecules or the polarity of molecules. So if a molecule is polar, it has what we call dipole moment. And the important thing about that is the electron distribution is not symmetrical. So if you think of it as either a teeter-totter, if you've ever been on one of these teeter-totter things with a sibling, got yelled at in trouble for letting them on or off, right? We're not evenly distributed. Or if you were lifting weights, if you had a bar and you had, a lot of weight on one side and a little weight on the other side, that would be uneven. Or if it's even, right? So if you have a bar, 45-pound bar, and a 45-pound weight on each side for a total of 135 pounds, it should be evenly distributed. So the weight, it feels like it's easier to pick up because 135 pounds all on evenly distributed with the center of gravity in the middle of the bar. Whereas if you had two 45-pound plates on one side of the bar and nothing on the other, the bar would be lopsided. It makes it much harder to pick up, especially if you're trying to hold it in the middle. Same thing with here. So the electrons, HCl is a polar molecule. Why? Well, remember the top 5 electronegative, right? That's a top 5 electronegative atom, right? It's fluorine, then oxygen, then chlorine, then nitrogen, then bromine. So what does that mean? That means that the electrons are being pulled around the Cl. So if you look at this picture on the right-hand side here, you have high electron density versus low electron density. That's a delta, Greek letter D, delta minus, delta plus. And so there is the charge, the electrons, right? The electrons are moving around the atom in the bonds. They're moving very, very fast. So they're spending more time over here on the right-hand side of the chlorine and less time over here on the left-hand side of the hydrogen. What that does is makes what we call a net dipole moment. So you have to have a net dipole moment. Going back to the bar here, if we have 45 pounds, 45 lbs's and 45 lbs's, that would be symmetrical. You have weight on both sides. And for some of us, that's a lot of weight. Some of us, that's not a lot of weight. But either way, it's symmetrical. If I add another 45 pounds to the right-hand side, it is now unbalanced. It's unbalanced. Now it's symmetrical. If somebody adds a 2.5-pound plate to one side, it's technically unbalanced. Might not notice you might notice it depending on the weight. But if you have, in this case, this would be 225 plus 2.5, right? So that would be 227.5 pounds. That would, with the orange 2.5-pound plate on the right-hand side, it would be slightly uneven, harder to notice. Another way I look at this is speeding, right? If you go speeding, 46 miles an hour and 45 mile an hour zone is technically speeding. 50 miles an hour and 45 is speeding. 55 miles an hour and 45 is speeding. 60 miles an hour and 45 is speeding. So they're all classified as speeding, but you know that a police officer, especially if you're nice to them, may or may not give you a ticket depending on how fast you're going. If you're going 60 and a 45, you're probably going to get a ticket. If you're going 50 and a 45, you're probably not going to get a ticket, especially if you're nice to the police officer. So there's different degrees of speeding in speeding, just like polarity. And we kind of talked about that with bond polarity. So now, compounds, if we're going to draw here, bent, trigonal pyramidal, bent, T-shaped, seesaw, and square pyramidal, those are always polar to some degree. Now, sometimes that's a 46 miles an hour in a 45 mile an hour zone. Barely polar. We actually call that more polarizable than polar. However, it's still not a symmetrical shape. Always polar. These are unsymmetrical shapes. And they have to be symmetrical in all their mirror planes, so to speak. So if you look at a human being, like you or me in the mirror, if you split us down exteriorly, if you split us down the middle from horizontally, if you split us down the middle vertically, we're pretty symmetrical, almost a mirror image of each other. But if you split us by the belt and the waist and belly button, we are definitely not symmetrical that way. So just because you might be symmetrical, what am I saying here is that bent is going to be symmetrical that way, but it's not symmetrical that way. So this first blue line here, that is symmetrical, that thick one. The one that just disappeared, it's not symmetrical. It's not a mirror. So that's what we're talking about when this. Now, all the other ones can be polar. So if I look at tetrahedral, as long as all four of those atoms, we got 1, 2, 3, 4 blue ones. As long as all four of them are blue, it's going to be symmetrical and it's going to be nonpolar. If we put a top 5 electronegative, it's polar. If I put a second top 5, it's still polar. Unsymmetrical. Third, still polar. Fourth, not polar. So that's what we have going on here. So let's look at these. So polar molecules, nonpolar molecules. Not symmetrical. Let's look at CO. Carbon has 4 electrons, oxygen 6 with 10 electrons. Polar bond, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Well, oxygen, of course, is a top 5. So what happens here? This will be slightly negative. This will be slightly positive, and we're going that direction. CO2, OCO, has 2 polar bonds. How many electrons? 4 plus 6 plus 6, 16 electrons. So fill in the octets of oxygen, and we're good to go here with the Wright-Lewis structure. Well, what we have is I have a negative, a positive, and a negative. So we have one going that way and the same size going that way. Looks like a tug of war. So I have a negative side in a terminal, central positive, negative terminal. It's a tug of war of electron density and no one's winning. The question is, even though I have 2 very polar bonds, is this a polar molecule? Well, it would be symmetrical. It's not much different than the barbell I had. If I had a lot of weight on both sides of the barbell, not just the bar in the middle, it looks like the outsides are way heavier than the middle. However, since it's symmetrical, it's evenly distributed, and you can lift it. Or in this case, it's nonpolar. The molecule is nonpolar because you need to have only 2 poles of charge, not 3 or 4. You got to have 2 poles of charge to be polar. Carbon dioxide does not. N2O and NO. Right. N2O has 5, 10, 16 electrons as well, except it looks like this. It's a triple bond. Right, 2, 4, 6, 8, 10, 12, 14, 16 electrons. There we go. Oxygen's -1. But even if you drew it like CO2, it doesn't matter. Why? Well, even though nitrogen's the top 5, oxygen's more polar. Right, so these oxygens are top 5. N's also a top 5. However, we're still going to have electron density that way because oxygen is more electronegative than nitrogen. Or the top 5 aren't all equal. BF3. Well, boron has 3 electrons. Fluorine has 7 times 3, so that's 24 electrons. F, F, F. 2, 4, 6, and you feel like that's 8, 10, 12. And you can see they're just full. 15, 16, 18, 22, 24. I have 3 top 5 atoms. Very polar bonds. Negative, negative, negative. Positive in the middle. However, the shape is trigonal planar. It's symmetrical. Therefore, it's not polar. Ammonia. 8 electrons. 2, 4, 6, 8. This is trigonal pyramidal, which means we'll have a negative side up top. Between all 3 hydrogens will be the positive side. That's over here. Methane. 8 electrons again. You do not have a top 5. 2, 4, 6, 8. And you do not have any of a symmetrical shape. Straightforward. BRF3 and water. So BRF3, the electron count, 28 electrons. Br is in the middle. F, F, F. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. 2 lone pairs. This is T-shaped. So that means I have negative there, and those in orange are canceling each other out. However, in red here, that is not canceling each other out. So you have polar molecule that direction. Water, 8 electrons, 2, 4, 6, 8. It's technically bent. So for water, you have in the middle, you have a negative, and you really don't have a negative on each hydrogen. It's really between the hydrogens. So that's water. Right. So over here, I had N2 next. N2 is just and it is a top 5. However, nitrogen, it's the same electronegativity, so it's linear, nonpolar. What else? XEF4. XEF4. 4 fluorines. So what we got? We have 2, 4, 6, 8. Electron counts. 7 times 4 is 28 and 8 is 36. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. This is square planar. As a square planar, all those bond angles are 90. So do we have top 5 atoms here? Yes. We have top 5 atoms. So the fluorines have a lot more electron density than the xenon. However, it is symmetrical, so it's nonpolar. That's how you determine if a molecule is polar or not. You have to look at the molecular shape and the electronegativity to see how the atoms are bonded, and if we're unsymmetrical or symmetrical. And that's how you determine polarity. Well, thanks for watching, guys, and we'll see you next one.